In the previous video, we have seen how to write channel matrix H for the MIMO case, and in this video, we will look at the statistical properties of H. But before that, we will look at the classical IID channels. So what we mean by IID is, IID means independent and identical distributed. So to have classical IID channels, the first assumption is that the delay spread should be negligible. That means tau RMS is equal to 0. And this implies that the delays corresponding to each of the multipath is equal to tau hat. That means all the delays are equal. And this is the scenario when we have flat fading conditions. So that means the first assumption is that we need to have flat fading scenario. Then the second assumption is that H is modeled as zero mean, circularly symmetric, complex Gaussian with unit variance. And what it means is each of the component of H has a zero mean, then then complex Gaussian. Complex Gaussian means that every element can be represented in form Hi plus JHQ, where Hi and HQ, they are real Gaussian distributed with zero mean and same variance. And also this Hi and HQ, they are independent. Why? Because in the previous we have seen that when we take the cross correlation of Hi with HQ, it comes out equal to 0. That means Hi and HQ are independent. Now circular symmetric, if it follows the property that expectation of Ej phi of H is equal to Ej phi expectation of H. If it is satisfied this property, then we say that it is circularly symmetric. So the two assumptions of this classical IID channels are, first, we need to have a flat fading, and then the second, the H should be modeled as a zero mean, circularly symmetric, complex Gaussian with unit variance. And it also means that every element of the H has zero mean, every element has a unit variance, and every element is independent to the other element. That means if this is the channel matrix, if we pick out any two values, they will be uncorrelated. So as a result, this HW matrix is a uncorrelated matrix. So now we have also seen that if we have two antennas and the distance between the two antennas is greater than the coherence distance, then we say that these two antennas, they are uncorrelated. Whereas when distance is less than the coherence distance, there is some correlation between the two antenna elements. And this correlation is defined by the covariance matrix. That is R, denoted by R. And this expression states that if we have an uncorrelated matrix HQ, and if we know how they are correlated, then we can always generate a matrix, channel matrix H, which has a correlation. And also the properties of R is, first, that the R is positive semi-definite. That means all the eigenvalues, they are greater than 0. And second one, if R is equal to the identity, then in that case, H will be equal to HW, as if there is no correlation. And if we want to compute the covariance matrix, we can also compute it using this formula. Vectorization, taking vectorization of H multiplied by the Hermitian vectorization of H and taking the expectation of it, we can get the covariance matrix. Now the covariance matrix can be split into two parts. First is the covariance matrix at the receiver that determines what is the correlation at the receiver side, and this RT determines what is the correlation in the transmitter side. And if we know the correlation at receiver, we know the correlation at transmitter, and we have the spatial void matrix, we can always generate a matrix that shows the correlation between the elements. And R, the overall covariance matrix, is equal to the Kronecker product of the covariance at transmitter and covariance at receiver. Now to understand what is Kronecker product, let us say we have a two matrix, matrix A, which is of dimension n cross p, and matrix B of dimension m cross q. Kronecker product means every element of matrix A is multiplied by every element of matrix B. So that means the first element is multiplied by matrix B, the second element is multiplied, and so on. So as a result, the Kronecker product AB will result in the dimension Mn cross QP. Now in this case, if RT, let's say if we assume that there are empty number of antennas at the transmitter, then RT will be MT cross MT, RR will be MR cross MR. Then using this, we can write it as MR MT cross MR MT. This is the dimension of the overall covariance matrix R. And the HW, the properties of HW is, the HW is a full rank matrix with probability 1. And if HW is random and if there is some correlation, then in that case HW is not a full rank matrix. And how do we define a rank? Rank is defined as the minimum of number of antennas at the transmitter or number of antennas at the receiver, or we can say number of independent rows and columns of the matrix. And this rank is directly related to the multiplexing gain or capacity. We will see it later how they are related to multiplexing gain and capacity, but for now let us assume that the rank, higher the rank, the higher will be the capacity, and as the rank decreases, the capacity will decrease. And why this happens, this we will see it later, but for now let us remember this. So now we need to find out what is the impact of spatial correlation. So first, when there is a receiver side spatial correlation, that means when there is a receiver side spatial correlation, then HW will not be a full rank matrix, the rank will decrease, and so there will be a degradation in the capacity. Now whereas when we have a spatial correlation in the transmitter, so there may be two cases. First, the transmitter is informed with the correlation, or the transmitter is uninformed about the correlation. When the transmitter is informed about the correlation, then in that case we can design precoders to improve the capacity, whereas when they are uninformed, then there will be a degradation in capacity. So now the matrix H can be decomposed using the singular value decomposition, which is given in this way. H is U D V Hermitian, where U and V, they are the unitary matrix that follows this, where U Hermitian is equal to V Hermitian V is equal to IR, and R indicates the rank of H. And D is a diagonal matrix that contains the singular values of matrix H. And these singular values, they are always greater than or equal to 0, and they are arranged in a decreasing order. So then if we compute the H Hermitian, then also we can decompose into Q lambda Q Hermitian, where lambda is again a diagonal matrix which contains the eigenvalues of H Hermitian. And similar to the singular values, eigenvalues, they are greater than or equal to 0, and they are arranged in a decreasing order. Now either you compute the singular value of H or you compute the eigenvalues corresponding to H Hermitian. They both are related to each other in this particular way. The lambda I is equal to sigma I square, where I goes from 1 to R, rank of the matrix, and for I greater than the rank of the matrix, it will be equal to 0. And this lambda I gives us what is the strength. It gives us the indication about the strength of the channel. Next important property is square Frobenius norm of H. It is denoted in this way, and it gives us what is the total power gain of the channel. And if we have a matrix H, this is the first element, H11, HMR, 1, H1, MT, and HMR, MT. If we have a channel matrix H, then if we compute the square of each of the element and take the addition of it, then we will get what is the total power gain of the channel, or what is the total strength in the channel. And this can also be computed while taking the sum of all the eigenvalues of H Hermitian, and this will also give us what is the total power gain of the channel. So there are two ways to compute the square Frobenius norm of the channel. And the statistical properties of the square Frobenius norm determines the diversity performance of MIMO, and we will see it later how it determines the diversity performance in the coming lectures. The PDF of the square Frobenius norm when H is equal to HW, that means there is no correlation. It is defined in this particular form, which follows a chi-square distribution with 2 MRMT degrees of freedom. For the CISO case, earlier we have seen that it is chi-square with 2 degree of freedom. So now we have MR number of antennas at the receiver and MT number of antennas at the transmitter. So here in this case we get 2 MRMT degrees of freedom, and this is the important point to remember.